Okay, so we can semi-equivalently consider the notion of power. So power is energy used or work done over time. So we would measure that in watts. So maybe you've seen appliances that say this many watts or this many kilowatts of energy or power is required in order to run that appliance. Well, 1 watt is 1 joules per second. So remember we talked about energy being measured in joules, right? So power is measured in joules per second because it's the rate at which energy is done. And you can also see it expressed as force times velocity cosine theta, because if we express the change in energy as the work done, right, over time, we can say that work is equal to F times S cosine of the angle theta. And because we've got a delta T, we can actually divide that delta T by that. And what's S divided by delta T? Well, that's just going to be velocity. So if F times, we get F times V, or Fs over delta T cosine of the angle theta. It's like pulling out those two other factors common. And then so S over delta T is just the velocity, so Fv cosine of the angle theta. So we get power equals to Fv cosine of the angle theta. And so we're done. Yep. So we typically use this formula to analyze energy use required to move against forces, so e.g. raising something up against gravity. So this formula here, for example, if you use lifting something up with a rope, which is 1 kilogram heavy, right? The force due to gravity is about 10 newtons or 9.8 newtons, and let's say we're lifting it up at 1 meters per second, and so here the angle between the weight force and the velocity vector is actually 180, so the power is force times, so force of 9.8 times the velocity of 1 meters per second, cosine of 180, or we can say that they're almost parallel, they're anti-parallel, so cos 180 is negative, so we can say the power required is, if we take the magnitude of it, force of 9.8 times velocity of 1, so force times velocity is 9.8, so 9.8 watts of power.